describing how it could be programmed for a number of tasks. It is thanks to this single document that Ada Lovelace, as King is usually known, has gained the reputation of being the world's first computer programmer. There is no doubt that Lovelace succeeded in bringing the potential of the engine to a wider audience, though the degree to which she was indeed the first programmer has been disputed. One certainty is that the machine these instructions were intended for was never built. Realistically, it could not have been constructed with the mechanical tolerances of the time. And so, strictly speaking, we should say that the document contained algorithms in the form of tables that reflected the structure of the engine rather than computer programs in the modern sense. Algorithms are structured instructions that could be anything from the sequence of actions required to brew a cup of tea to complex manipulations of data to solve a mathematical problem. They don't require any computer. They can be worked by hand, but can, as was the case here, be structured in such a way that they fit well with a computer's architecture. Unfortunately, in the entirely desirable urge to provide good female role models from the past, Lovelace's contribution has been exaggerated. Lovelace was the daughter of the poet Lord Byron and Annabella Milbank. As a child, Lovelace was encouraged by her mother to study mathematics. She is often described as a mathematician, but it would be accurate to describe her as an undergraduate-level math student. From letters between Babbage and Lovelace, it seems well established that the notes that Lovelace added to Menabrea's work were strongly influenced by Babbage. And even taking algorithms as programs, we know that Lovelace was not the first. This is because, as historian of science Tony Christie points out, the Menabrea memoir that Ada had translated already contained examples of programs for the analytical engine that Babbage had used to illustrate his Turin lectures and had actually developed several years before. The notes contain further examples from the same source that Babbage supplied to the authoress. The only new program example developed for the notes was the one to determine the so-called Bernoulli numbers. We do know that Babbage, in his lectures, described algorithms that could have become programs for the analytical engine, had it ever been built. Usually, with a totally new piece of technology like this, we have to wait for some kind of prototype to be constructed before we can be certain of the device's capabilities. But remarkably, the analytical engine algorithms clearly showed the remarkable power that the machine would be capable of had it ever been built. Rather than wait for programs to be developed, the engine could instantly leap into action. Having algorithms that were ready to go on a technology that was impossible to construct at the time was remarkable. That such a thing should happen twice seems even more surprising. Yet 153 years after the publication of Lovelace's translation and notes, a very similar occurrence would play out. This time, the imagined engines in question would invoke the power of the quantum. Program 2, 1996. By 1996, electronic computers had been part of government and business establishments for decades and had become relatively commonplace in homes, since personal computers moved from the realm of enthusiasts' toys to commercial products in the 1980s. Unlike the analytical engine, electronic computers were too complex to be designed by a single person, and although some early programs were the work of an individual, many were constructed by teams. Although the underlying concepts behind the electronic computer would continue to be developed, and these devices would continue to become increasingly powerful for decades to come, by the 1990s, scientists were already aware of limitations in the way that such computers worked. 15 years before our key date, the physicist Richard Feynman had speculated about constructing computers where the basic unit of operation was not the traditional bit, which was limited to holding values of 0 or 1, but rather a quantum bit, based on a quantum particle such as a photon or electron, which could be in an intermediate state with a potentially infinite set of possibilities. By the 1990s, teams were thinking about or attempting to construct such quantum computers. The challenges they faced were huge. In 1996, ability to manipulate individual quantum particles was in its